Hello guys, welcome back once more to my YouTube channel Gamma Di Gamma. In this video I am going to solve another problem from the Romanian mathematical magazine. But this time instead of being an infinite sum it's a definite integral. So let's get started. We have I equals integral from 0 to 1 0 to 1. So on a unit square domain ln x times ln x y divided by 1 minus xy dx dy. So before we actually do anything, I want you to notice that we can always interchange the x and y coordinates. So instead of having an x here, we could have had a y, and the interchange does not affect this product xy, neither does it the denominator. And the domain is also very conducive, very nicely behaved under such a swapping of variables, because the limits and the order of integration is basically preserved. So we have integral 0 to 1 0 to 1 ln y times ln xy over 1 minus xy dx dy. So we have this line 1 and line 2 which are equal to the same thing I. We can add both of them. The advantage of doing that is we have 2I equals integral 0 to 1 0 to 1 ln xy from before, the common factor, and we have ln x plus ln y over 1 minus xy dx dy. The advantage of doing this, and I repeat, is ln x plus ln y becomes ln xy using the properties of logs. So we have ln xy and ln xy, so that becomes ln squared xy divided by 1 minus xy dx dy, again on the unit square domain of integration. It is at this point where we would like to allude to an identity from the very last video involving the integration on unit hypercube of a function which had product in its arguments of the n coordinates that we're integrating over, equaling integral 0 to 1 of the same function, but now with a negative ln u to the n minus 1 over n minus 1 factorial du. That's the identity. If you don't know where this came from, please watch the last video. I have proved it nicely by induction, considering the base case, the inductive case, and doing it quite nicely. So if we use this for the case n equals 2, because we have integral over dx dy rather than n unit hypercube, we get 2I is, using the identity, integral 0 to 1 ln squared u over 1 minus u, and we have minus ln u to the 1 over 1 factorial du, which you can easily simplify because minus ln u to the 1 is itself. So you have minus integral 0 to 1 ln cubed of u over 1 minus u du. At this point, you can realize one of the older methods that we have used throughout this channel is when, if you have a denominator like 1 over 1 minus u and u is in the range 0 to 1, or absolute value of u is less than 1, that's the radius of convergence, which is indeed satisfied because we're going from 0 to 1. We can write this as an infinite geometric series. So we have sum and the integral we can interchange by the dominated convergence theorem, minus sum k equals 1 to infinity, integral 0 to 1, u to the k minus 1. So this u term is actually the infinite geometric series term, which is coming from the 1 over 1 minus u fact term here, ln cubed u du. And now just integrate by parts without anything better to say about this. So we have minus sum from k equals 1 to infinity, u to the k over k ln cube u from 0 to 1, minus 3 over k integral 0 to 1 u to the k minus 1 ln squared u du, where this the second term So we're just taking the antiderivative of u every time while we take the derivative of the ln cubed in this second term, which involves the integral in it. That's just classic integration by parts. We've never taken an antiderivative of an ln function, so why should we here? Simplifying, we can do L'Hopital's rule for the zero, for when u goes to zero, but you should see that it actually vanishes. So all that remains is to do by parts of this second surviving term. So we get sum from k equals 1 to infinity, 3 over k squared now, u to the k ln squared of u from 0 to 1, minus 2 times integral 0 to 1 u to the k minus 1 ln u du. And again, this evaluated term without the integral vanishes. So we just have sum from k equals 1 to infinity, minus 6 over k cubed now, u to the k ln u from 0 to 1, minus integral 0 to 1 u to the k minus 1 du. And the first term again without outside the integral vanishes. And we just integrate this, which is probably the simplest integral you can do. So we get 6 times sum from k equals 1 to infinity u to the k over k to the fourth, evaluated from 0 to 1, which is just sum from k equals 1 to infinity of 1 over k to the fourth, which is Riemann zeta of 4 times 6. So we have Riemann zeta of 4, we know is pi to the 4 over 90. So that just becomes pi to the 4 over 15. And this was actually 2i, if you remember. If you recollect, this was all 2i. So we just divide by the 2 to get I is pi to the 4th over 30. Actually, that solves the problem for us. But I'm sure someone would have commented if the comments were still enabled. Is at this stage when we have when we use the identity, we end up with a ln cubed u over 1 minus u du. You could have argued, if you've been an avid follower of this channel, that why could we not use some special functions? You're right, actually. Here's the alternative approach. We use this identity involving a polylogarithm. So polylog of s plus 1 of z is z times minus 1 to the s over s factorial from 0 to 1, ln to the s of t over 1 minus tz dt. The proof of why this becomes the polylog is you can do the Taylor, the geometric series expansion of this 1 over 1 minus tz term, and you shall recover the infinite sum representation of the polylogarithm of s plus 1 evaluated at z, which is just sum from k equals 1 to infinity z to the k over k to the s plus 1. In our case, let's just set z to 1 and s to 3. We get li 4 of 1 is minus 1 over 3 factorial integral 0 to 1 ln cube t over 1 minus t dt, which we all know from before is just sum from k equals 1 to infinity 1 over k to the fourth. And this exactly was the integral we had there on top, which was minus sum from 0 to 1 ln cubed of t over 1 minus t dt, which according to our formula, our identity here, is 6 times the Riemann zeta of 4. This right hand side here is the Riemann zeta of 4, which again turns out to be pi to the fourth over 15. And of course, then we divide by the 2 because that was 2i. So that solves the question, guys. I may have rushed a little bit over this entire thing, but the idea is simple. You add both of them, you introduce this function that is purely um, has products of the arguments, so that we can use our nice identity from our arsenal that we recently added, and then just simplify it nicely using our standard techniques of integration, either the geometric series, or if you remember, if you know the formula of the polylogarithms, essentially. And that is the approach. We just destroy this crazy looking integral, seemingly crazy looking integral, using our nice powerful identity. So that's it for this video, guys. Please like, share, and subscribe to my channel. Recommend me to your friends and keep doing math. Peace out.